All right, loud and clear. If there's anything specific you want to chat about or work on while recording, just let me know. I'm ready when you are.
So let's see what quantum computing architecture, hardware, simulations, and all those things combine. Can you help me to understand if I want to design a specifically quantum computing architecture that would solve a specific problem for a sample of qubit system?
Designing a quantum computing architecture for a specific problem is all about matching the problem's structure to the strengths of quantum algorithms. First, you'd think about your problem, like factoring, optimization, or simulating quantum systems. Then you pick an algorithm, like Shor's for factoring or QAOA for optimization. Once you know what you're aiming for, you'd consider the qubit system, how many qubits you need, error correction overhead, and the connectivity between qubits. You'd also think about hardware, whether superconducting qubits or trapped ions fit better, and simulation stages to test it before real hardware. It's basically a dance between algorithm, qubit resources, and error handling, all tailored to what you want to solve.
The dance between algorithm, qubit resources, and error handling. It's a intriguing fact.
It's really about balancing all those moving pieces. None part works in isolation. The algorithm might say, I need these operations, while your qubit architecture responds, I can do that, but mind the noise. And your error correction chimes in, I'll protect the delicate dance steps. In the end, you choreograph all these elements to solve something classical machines struggle with.
Can you uh, defeat your comment with the classical computer and the and the quantum physics behind all those things?
Sure. In classical computing, you're basically flipping deterministic switches. Bits are either 0 or 1, and logic gates manipulate them predictably. Now, quantum computing leans on quantum physics. Qubits can be in superpositions, both 0 and 1 at once, thanks to quantum states. They also get entangled, meaning their states are deeply correlated. When you design a quantum architecture, you're harnessing these weird quantum effects to do certain computations, like factoring large numbers or simulating molecules, much faster than classical machines. But you also have to deal with the fragility. Quantum states can decohere, hence the need for error correction. So you're building a physical system where quantum physics directly shapes the logic, and the challenge is keeping those delicate quantum effects alive.
Oh, that's what the superposition state and the measurement collapse is what we are we have to protect it from, because when we prepare a state, we need to think that that state will be preserved. Any
Exactly. That's the heart of it. When you prepare a quantum state, you want it to evolve under your algorithm's logic without outside interference. The environment or even a measurement can collapse that superposition, ruining the quantum magic. That's why we have to protect the state, whether by isolating it well, controlling the operations precisely, or using error correction. In a sense, you're creating a delicate temporary bubble of quantum coherence to get your problem solved before it pops.
But that state is evolved in a specific hardware, superconducting qubit or a trapped ion or a photonic or NMR like thing. How how the error and noise like the state collapse thing happen?
So every hardware platform, whether it's superconducting, trapped ions, or photons, has its own environment. Tiny interactions with that environment, stray electromagnetic fields, thermal fluctuations, even cosmic rays, can measure or disturb the qubit. That's what collapses the quantum state, like forcing the coin flip to land as heads or tails. Errors happen because these disturbances slightly nudge the qubit out of the intended state. Each hardware has different noise sources. Superconducting qubits might struggle with microwave noise, trapped ions with laser precision. That's why quantum error correction is vital. So you can keep the quantum dance going even when the world tries to peak.
Okay, okay. Suppose I want to make a one qubit system that would tell me either my spin of an electron. So, can you frame the complete architecture as an example and intuitive thought to understand the large scale picture of quantum computing?
Sure. Imagine you want a single qubit that tells you if an electron spin is up or down. Your qubit could represent the electron spin state, up as 0, down as 1. In a superconducting setup, you'd have a tiny circuit that can place this qubit in a superposition, both spin up and spin down at once. You'd design control pulses, microwaves in this case, to manipulate that state and measure it. When you measure, the superposition collapses to spin up or spin down, giving you the result. Now scale up. Instead of one qubit, you have hundreds, each representing more complicated quantum information. You'd need intricate dates to entangle them and run algorithms, and because noise threatens your delicate states, you'd have error correction schemes that protect these larger computations. In short, that single spin qubit is just a stepping stone to orchestrating vast entangled systems, solving problems no classical computer could.
So, simply you are telling that we need to find the electron spin up as 0, down as 1. So in a superconducting setup, so we have a tiny circuit that can place this qubit in a superposition state. First we have to make that state in a superposition state, both spin up and spin down at once. And we have to design a control pulses, that is the microwaves. In this case we have to manipulate that state and measure it. So when we measured, the superposition collapses to spin up and down, and then we are giving the results. Okay.
Exactly, you've got it. That's the basic idea. And when you scale it up to many qubits, you're doing similar things, but in far more intricate patterns. That's the heart of quantum computing, building on that simple qubit intuition to tackle huge complex problems.
Okay, in this electron spin case, how the errors and noise I need to tackle, and what are the methods I will use? Because you only mentioned about this error that might the noise, that is the environment, if that state somehow, but designing a superconducting qubit, it's so precise, and their architecture is very high level.
You're absolutely right. Superconducting qubits are finely tuned, but errors creep in. The main culprits are decoherence, the qubit losing its quantum state over time, and gate errors, imperfections in your control pulses. To tackle these, you employ quantum error correction, encoding a single logical qubit into multiple physical qubits so errors can be detected and corrected. You'd also use dynamical decoupling, pulsing sequences that help refocus the qubit and reduce noise. And of course, you design the architecture to shield qubits, cryogenic temperatures, isolating from stray fields. In short, it's a mix of clever engineering, active error correction, and careful pulse design to keep that quantum state alive.
Okay, now can you tell me what we have discussed till now?
We started with the big picture of quantum computing architecture, focusing on how you match a problem to quantum algorithms, qubits, and error correction. We then used a simple example, measuring an electron spin as a qubit, to illustrate how a qubit can be prepared in superposition, controlled, and measured. After that, we talked about scaling up to larger systems, where you entangle more qubits and handle noise. Finally, we discussed sources of error like decoherence and how quantum error correction, dynamical decoupling, and careful engineering help keep the quantum state intact for reliable computation.
Okay, thank you.